limits. So this is the start of calculus. Calculus is really the study of four things. You got limits, derivatives, integration, and sequence and series. Now, if you ever take AP Calculus studies heavily on the first three, limits, derivatives, and integration. BC Calculus is all four. That's the difference between AP and BC. They do this whole extra part of sequence and series, which is like a half year. IB, we're going to really focus on derivatives and integration. We're going to touch on limits, and that's what today and the next lesson is. But we're really going to focus on derivatives and integration. So these are all the study of calculus. So let's get started with what a limit is. So by the end of this lesson, the goal is to be able to read limits from a graph like we have here. Read limits from a table, which is the easiest one. Read limits from a function of a given value. So if I'm going to give you a function like what's f of x plus 3, what's the limit of that at certain values? And then be able to find the limits at infinity. That's like a whole special type of limit. So what a limit is kind of different. A limit is what's it look like it's happening to a function at a certain value, right? Not what actually happens. If you look here, there's a hole in the graph. Limit's not going to care about that hole. It's going to be like, oh, it looks like it's going to a certain number. That's all limit cares about. So let's look at this first one here. This is how the limit reads. The limit as x approaches 3, right? That's what that arrow means. As you get close to 3, as you approach 3, what's going on to your function? What's the y doing? Like that's what it's asking. So let's look at 3 here. I like to do like this. So here's 3. Sort of straight line, right? As you get close to 3 on your x, right? As you're getting close to your 3 on your x, let's look at it from side by side. Let's look at this side here first. As you get close to 3, what's your graph doing? What's your y doing? Well, as you get close to 3, right, as you're getting close to this one, your graph's look, it's going here. It's going close to 4. Now, that's from the left side. Let's look at the right side. Same idea. As you get close to 3, going like this, what's my graph doing? My graph's going like this. It's also getting close to 4. So my limit's just 4. Right? As you go from left, you go from right, you get 4. Even the value there, right? If I ask you what's f of 3, right? You just look what's the y value. You go, oh, it's 4. So the limit's 4. The limit as x approaches 3 is 4. Because as you go from the left side, you go from the right side, it's both 4. Now I said a little earlier, limit doesn't care what actually happens at the spot. Just as you get close to what's happening. What does it look like it's happening? So let's look at 4. That's a little different. Before we do that, let me erase these so we have some clear thing to work with. That's some good erasing. So the next one, limit as x approaches 4 with a little minus sign. Look what's going on there. Well, the minus sign is just a very specific limit. It means from the left. We only care about from the left side. So let's look at it. So as x approaches 4. So again, notice it says as x, that's a much worse line than before. Right? As x approaches 4. So keep in mind it says as x approaches 4. So here's 4. As we're getting close to 4 as we're getting close to 4 on the x, what's the y doing? That's what I want to know. So right, this is a minus sign, means from the left. So let's look at what's going on this side. So as you get close to 4 on the x, what's my y doing? Well, my y is getting closer, looks like to 5, right? On this side, looks like it's going toward 5. Now, as you probably guessed, if minus means from the left, plus means from the right. So as you're coming from the right, as I get close to 4 on my x, what's my y doing? Well, it's a straight line going toward 5. So here's the thing about limits. If the left side limit and the right side limit match, that's your limit, right? Look at this. From this side and from that side, they both look like I'm going toward 5. That's my limit. Limit doesn't care what happens. This is what it looks like it's going to happen. It looks like it's going toward 5. It looks like it's going to be 5 at that value. So that's your limit. Now again, limit doesn't care what actually happens, right? F of 4 says, what's the value at 4? Well, the value at 4 is right here, which just happens to be 4. These don't match, that's fine, right? Limit doesn't care. Limit just wants, hey, what does it look like it's happening? That's kind of the basic idea of a limit. Let's do a few more examples. So let's look at this one. Let's do the same idea. All right, let's look at 2. So we're going 2 from the left, 2 from the right, and 2. So here's 2 on my x. I started off pretty good. The limit as x approaches 2 from the left. So remember, we're going from the left side. So follow your graph on the left side as you get close to 2. It's going close to 0 on the line. So that's going to be 0. The limit as x approaches 2 from the right. So we're coming from the right side. Also getting close to 0. These two things match. So my limit's 0. And it also makes sense. Look at it. From left to, it's just a straight line. 2, 2. Actually, I should go down here and do f of 2. Right, what's the value at 2? Well, there's a point right there. It's a line. So 0. Right, limits are supposed to be that easy. When it's a straight line, when there's no something special about it, what's the limit at 5? 6. Right, that's just the limit. The limit's the same thing as the value when it's a straight line. But when it gets interesting, is when there's an issue there. What we call a discontinuity. Look at this. All right, so let's talk about that one. So let's look at the limit. Let's look at the limit at 3. So let me draw a little dotted line so we can kind of see it. You could see the partition better. Right, limit for 3 from the left. Again, that means that as you get close to 3, what's your y doing from the left side? So my graph, look where the graph's going. It's going, looks like, let's say 1. I doesn't say 1 or 2, but let's say it looks like going to 1. That's from the left side. Look at the right side. Right, so here's 3. As I come from the right side, what's my graph doing? It's going to 4. They don't match at all. One's going to 1. It looks like a negative. Let me cross that out. One's going to 1. One's going to 4. They don't match at all. So when this happens, everybody's favorite limit does not exist. Right? So there's no limit here, right? Because remember, the whole idea is what's the graph? What does it look like it's doing? Like over here, it looked like it was going. You know how to open circle? It looks like it was going toward 5, both directions. Here, I have no idea what it's going to. One's going to 4, one's going to 1. It doesn't look like they're going to any single number at all. So limit does not exist. And then for a little review here, what's f of 3? Remember, f of 3 is the closed circle, so f of 3 would be the 1. Let's move on. Let's do a few more. Hopefully we get the idea. Like really cemented in. Limit as x approaches 3 from the left. So again, here's my limit. Here's 3. That's my terrible line, as always. Classic Fregoso. So sad. So limit as x approaches 3 from the left. Right, so again, here's the left side. Look what your graph's doing. It's going all the way down there. We call that negative infinity. Back when I was at school, they call that negative. No, that was terrible. Now let's look at 3 from the right. Right, so same idea. Here's our 3. Here's the right side. What's our graph doing? Right, as x approaches 3 from the right, what's the y doing? What's the graph doing? Also negative infinity. So remember that general idea if you're looking at limits from a graph, if the left side and right side match, that's your limit. In AP Calculus, we'll go a little more detail into this, but for us, we're fine. That's negative infinity is fine. And then what's f of 3? Remember, what's the value at 3? In this case, closed circle. So it looks like 1. Right, and that's the limit. Left side, right side. Look at it. Let's do one more on the graph. So look, here we're looking at 0. Limit as x approaches 0 from the left. So again, here's my graph. Blah, blah, blah. Now we're trying to get to 0 from the left. So follow your graph. It's going toward 1. Graph from the right-hand side. Right, so again, coming from the right, what's your graph doing as you get closer to 0? Also looks like 1. They match, so your limit is 1. G of 0, what's basically saying what's the closed circle there? 0. And that's how you read limits from a graph, right? Reading limits from a graph is just look at both sides. If they match, that's your limit. If they don't match, like over here, then you could be all happy until the limit does not exist. Yes, we call quote mean girls. So next, reading limits from a table. It's essentially the same idea, right? So this one's already kind of done for us. here's our x values. So what we're looking at, notice how 1's undefined. We're looking at this one. We're looking at the limit as x approaches 1. So we're going to kind of do the same thing. We're going to get close to 1 from the left, so below numbers. As we get close to 1, what's going on? Look at the values here. They're getting close to 2. So as you get close to 1 from the left or from below, right, it looks like we're getting close to 2. As you get close to 1 from the other side, from above, from the right, look at the values. It's also getting close to 2. So they match. My limit is 2. You can also see here, there's a graph, right? Here's 1. Limit from the left. Limit from the right. They're both going toward 2. Again, remember, I don't care what actually happens at 2. Just what does it look like it's happening, right? If I ask you what's f of 2 here, there's no value. It's all empty. V does no value. Does not exist. Let's do a few more of these real quick. Let's look at this one. The limit as x minus 2 over x squared minus 4 as x approaches 2. Again, so we're looking at 2. All we have to do is look at both sides. As I get close from below it, right, as I get closer to, what's my graph doing? Look at 0.256 to 0.2506, 0.25006. Doesn't look like it's going to 0.25. And as we look at numbers above 2, or 2 from the right, as we get close to 2, it's coming this way. Look at our graph. 243, 2.249, 0.2499. I could talk. Again, also getting really close to 0.25. That's our limit, 0.25. Same idea here, right? Look at this ugly mumbo jumbo. Who cares? As you get from the top, 4. What's my graph doing? Looks like 0.04. As you go this way, maybe 0.05, but whatever. 4. Look what my graph's doing. 0.00, 0.03, 0.04 looks like it's going toward. They match. That's your limit. Right, so it's kind of the same idea. Look at it from the left side, look at it from the right side. If they match, that's your limit. Right? Again, limit doesn't care what's happening at the actual value. Just as you get close to it, what's going on. Let's do one more of these. Limit as x approaches 0 of absolute value of x over x. Now look what's going on here. So again, notice how we're getting close to 0. That's what I care about. So here's 0. Let's go for 0 from the left, below. Look at, they're all -1. So my limit's -1. Right? Then here, as you get close to 0 from below, right? Look what your value's in. These are our +1. Those things don't match. So, our favorite, limit does not exist. Yay. Now let's move on to how to find limits given a function. Number tables, number graphs, just like arithmetic stuff. So finding limits given a function. Well, actually, preface the non-infinity type. It's different with infinity. So number one rule of finding limits to a given function. The number one rule is step 1, I should say. Step 1. Plug in the limit. Or sub in the limit for people who want to be mathematically correct. Plug in the freaking limit. Because what happens is if it works, you're done. If you get a number, which just means you get a number, you are done. That's your answer. That's the limit. If it doesn't work, so what does doesn't work mean? If you get 0 over 0, that's called an indeterminate form, then you have work to do. Then more work to do. Move on to step 2. I kind of combine work and more to mork. I meant more work. Let's try and be efficient, man. More work to do. And this is really where we differ from AP Calculus. AP Calculus spends a lot of time on all different ways you could fix a limit. IB, a little easier. What's some more work to do? How do you try to fix it? For us, really, all it's going to come down to is to factor. Once you factor and stuff cancels, then you can plug it in again. So let me show you an example, or 3 examples, and then more examples. So a lot more than 3. More than 3 examples. So look at A here, right? Limit as x approaches 2 as x squared. So you know what I do? I plug that freaking limit in. So I'm going to get 2 squared. I should actually write this. The limit as x approaches 2. Plug it in. 2 squared. It's a 2, not a 1. And I get 4. Not 0 over 0. I'm good. That's my answer. Done. Life's great. Answer's 4. Right? Let's move on to the next one. B. Plug in 0. So the limit as x equals 0. That's just technical. 0 squared plus 3 times 0 over 0. And sadly, I'm going to get 0 over 0. Right? That's sad. I could get 0. 0 is a good answer, but 0 over 0 is bad. I got to work. I got to fix this. So, remember, we're in IB. Only you have to worry about fixing is factoring. Notice the top both have an x. So let's write this. Limit as x approaches 0. Factor out the x from the top. X plus 3 over x. These cancel, because that would be a hole in the graph. And now you can plug it in. Plug in 0 now. 0 plus 3, and you get 3. That's the limit of this function. It's 3, right? Beforehand, we had a hole in the graph. That's why there was issues. But now, to get rid of that hole, x equals 3. Limit's 3, not x equals the limit's 3. All right, let's look at C over here, right? Same idea. Step 1, plug in the freaking limit. So I'm going to get, let's do it right here, 3 squared minus 9 over 30 minus 3. Again, I get 0 over 0. So that means you have work to do. We have to factor. So let's go limit as x approaches 3. Hey, the top's the difference in two squares. Don't we love algebra? That's x minus 3, x plus 3 over x minus 3. These cancel. And now you can plug your 3 in. We get 6. Right. That's really it. For finding limits of given function, that the non-infinity type, all you have to do is plug it in. If it works, you're done. If it doesn't work, you got to fix it. And for us, that encompasses factoring. When you get to AP Calculus or just calculus in general, it's encompassed a lot more things like conjugates and rules and theorems. But for us, we just got to factor, baby. So let's look at a couple examples here. I'm going to ignore the fact that I said baby. So over here, limit as h approaches 2 of 7. Now notice how step 1, plug it in. There's nothing to plug it into. There's no x. That's great. It's a constant. Your answer is just 7, right? You can't plug anything into it. Your answer is just 7. Right? The limit of a constant's always going to be the constant. So the limit as x approaches anything of some constant k is just k, because you can't plug anything in. So it's just the k. Look at here. Limit as x approaches 4. Plug that 4 in. Right? Plug in the freaking limit. I get 12 minus 1 and 11. Done. C. Plug in 0. You can see already it's been issues, right? 0 minus 0 over 0. 0 over 0. So that means we got to factor. That's the only way we know how to fix it right now. So you can factor out the x on top. 2x minus 1 over x. These cancel. And now you can plug your 0 in. 2 times 0 minus 1. Negative 1. Get down here. Oh, shoot. They have an h there. Not scared. It's the exact same as an x. Do the exact same stuff. Plug in the 0. See if it works, right? Plug in the limit. Again, I get 0 over 0. So I have to work on it a little bit. Same rules apply. Hey, they both have an h. Factor out the h. Right, the limit as h approaches 0. So now they're gone. I can plug my 0 in because there's no more issues. 0 squared minus 8 or negative 8. Last one, right? Same idea. Plug in. Remember, first thing you always do is plug in the limit, because sometimes it's gonna work. People get so caught up in trying to factor and cancel stuff out, you forget. Hey, sometimes it works. Not in this case, I'm telling you right now, but in general, sometimes it works. 3 minus 3. This is 9 minus 9, so 0 over 0, which means I got to work on it. Let's factor this. The top is x minus 3, x plus 2, for x minus 3, as a limit as x approaches 3. These cancel. Plug the 3 in, and you get 5. By the way, if you're curious what's happening there, it's a graph with a hole in it. So you have a x plus 2 here. And at 3, because remember the hole is always opposite, you have a hole, and the hole's at 5. That's what's going on. Right? So at x equals 3, there's a hole in the graph, so that's why you can't just plug it in. But if you look at the limit, it's going to 5 in both directions. So that's what's going on. That's how you do it with the function. Non-infinity function. And since I said that, we're doing x. That's right, infinity functions. Or limits at infinities. I was saying that wrong. Limit at infinity. Just like with regular functions, we're going to look at limits at infinity 2 ways. Let's look at it by graphing first, and then we'll look at it with this a function. So when we look at graphing, so look at this one. The limit as x approaches negative infinity of x. So what does that mean? Remember, negative infinity is over here. So what's your graph doing? Looks like it's getting toward really close to 2. That's your limit. Look at this one. Limit as x approaches infinity of f of x. So remember, infinity's, now that's negative. This is infinity over here. What's your graph doing? Going close to 2. Now, if you notice, that's what's going on there? Well, these are my horizontal asymptotes. Because for the most part, a limit at infinity, as x approaches infinity, is just horizontal asymptotes of rational functions. That's what we're going to talk about. I mean, we'll get more into detail with that when we start talking about how to do functions, but that's all it is, right? That's what a horizontal asymptote tells you. As you go to infinity, what's going on? As you go to negative infinity, what's going on? So that's why limit infinity is the same thing. Let's get another graph. So graph of y equals 3x. Now, this is not a rational function, so that horizontal asymptote doesn't apply for both sides. Only applies to one side. So let's look at the limit as x approaches negative infinity. So let's think about it. Negative infinity is over here. Look at my graph. It's going down to 0, which is a horizontal asymptote. But it's not a rational function, so the same rules don't apply. If we look at the limit as x approaches infinity, here's infinity. Look what my graph's doing. Going all the way up to infinity. And that's how you find limits to infinity with the graph. You just graph it and then look at the endpoints, right? What's going on in infinity? What's going on in negative infinity? When it's a rational function, and then this is a horizontal asymptote, other functions, you actually got to look at it. Now let's talk about how to do it with the function. So like I said earlier, it's really just a horizontal asymptote. And if you remember algebra 2, the way you do horizontal asymptotes is just powers. So we look at the highest power. So and there was three choices. The top power could be bigger than the bottom power, and that would give you no horizontal asymptote. In our case, since we're doing limits, that's gonna give us either infinity or negative infinity, and we'll talk about it more in detail in a second. But for example, that'd be like x cubed plus 1 over x squared plus 2. Top power is bigger. So when that happens, we had no horizontal asymptote, but for limits, that's either no limit or infinity negative, which means the same thing. Limit has to be a number. It's like into the weeds thing, but we just say infinity or negative infinity. Now what if the bottom power is bigger? So it's like x plus 1 over x squared plus 3. Bottom is bigger. That's y equals 0. Or for us, the limit equals 0. And if they're the same, something like 2x plus 1 over 5x minus 3, that was the ratio of the powers. Basically, ignore everything except for the highest powers, and you take the ratio of them, so 2/5. So that's the ratio. And that's the general idea of how to do asymptotes, of how to do limits at infinity. All we're going to look at is the powers if we have a function. So if you have top power bigger than a bottom power, it's going to be infinity or negative infinity. If you have bottom bigger than top, it's going to be 0. And if you have them the same, then it's going to be the ratio. So let's do a few examples and then we're done. So this is the first one here. Again, all we're going to focus on, it's called the power rule. All we're going to look at is the powers. So essentially, it's the same thing as saying x over 3x. I should say highest powers. Hey, they're the same. And they also reduce. So you just get 1/3. That's the limit, right? So again, this only works at infinity. And notice on this one, they're the same power. All we want to look at is the highest powers. So look at myself, hey, they reduce 1 over 3. Next one, negative infinity. Now same idea. All we're gonna care about is the highest powers. So it's the same thing as saying x cubed over 3x squared. That actually reduces, and you get x over 3. Now again, the 3 doesn't matter. It's a 3. Who cares? But so what's going on? Is this infinity or negative infinity? Well, let's look what happens. You're plugging in negative infinity. So this is like negative infinity over 3. So essentially you're going to get negative infinity. Right? If you plugged in positive infinity, you'd get positive infinity. Right? It all works in the way it works. That made no sense, but whatever, I'm going to go with it. Not like everything I say makes sense anyway. So over here, a few more than before we're done for today. Limit as x approaches negative infinity. Again, look at this. All you have to care about is the highest powers. So 2x squared over x squared. Notice, hey, they're the same. They cancel out. You just get 2. That's your limit, right? If they match, it's just a ratio. So in this case, 2. I don't care if it's infinity or negative infinity. They match. That's all that happens. This one right here. Hey, another one. They're the same power. So let's look at those two. These cancel out. 3. Limit as x approaches infinity of 3 over x minus 2. Now again, highest powers. So in this case, I guess that would be those two. That's all we care about. Now, the bottom power is bigger. You're plugging in infinity. You're going to get 3 over infinity. That's why it's 0. It's 3 over a huge number. It's basically 0. So the limit, as you keep on going, is going to be 0. As it gets closer and closer to 0. Right? So don't forget our general rule, right? Top, bigger, and bottom is either positive or negative infinity. It all kind of depends on how it falls out. If the bottom power is bigger, 0 automatically. And if they're the same, it's a ratio. Now let's look at this one. Not as easy, right? It's not a rational function. I can't use the horizontal asymptote thing. I can't use that thing because it's not a rational function. This is an e. So the best thing to do here is just graph it. Right? If you guys remember how to graph, this moves it down. This moves it right. This is a basic e graph. Looks kind of like this, where it crosses that 1, where you're going to go down 3. This is always, by the way, this is always a horizontal asymptote, because normally it says 0. So we have a horizontal asymptote at negative 3. Then we move right 2. So 1, 2. And it's going to be kind of like this. I just need to sketch an imperfect graph. Now, look what it's asking for. It's asking for negative infinity. So at negative infinity, I'm getting really, really close to negative 3 because it's horizontal asymptote. So that's my answer. If it said positive infinity, I'll be going up to infinity. But with these, it's all about the horizontal asymptote, and that's always the vertical flip, the vertical shift. And then the last one here, right? Look at these two. Hey, they're the same power. I'll look at that. So x over 3x, that reduces to 1/3. There we go. That's it for limits.